We're going to look at the factors affecting the rate of a reaction, and it's probably useful if you looked at the information about collision theory first. And you're going to pause the video here and see if you can list some of the factors already. Just think about them and what they are. And then when we go on to look at the factors, you may have mentioned some of these and some that aren't on the list that we'll deal with as well later on. So we've got particle size. That's not the individual molecule size that's reacting, it's the sample. So you've got one sample that's a big lump, and then perhaps the same material that has been broken into smaller fragments or even a powder. Small activity here. Draw 3 boxes for each factor and put in for each factor 3 diagrams as to what is actually happening with the reaction to make the rate change with each of those in turn. So the first one we're going to look at is particle size. So again, it's looking at the same substance. So really we're looking at surface area and looking at the number of collisions which are possible because of the sample size that you've actually got. So we're going to look at a cube just to make the arithmetic a little bit more straightforward. And a cube has got 6 faces, and they're squares, and the one shown here is 1 centimetre side of each square. We're then going to look at 8 of those 1 centimetre cubes stacked together to make a larger cube of 2 centimetre size, and then we're going to break up those 8 cubes, and we're going to look at the surface area of the 8 cubes. So what's the total surface area of each one? Pause and do a little bit of a calculation. And here we have, for a single cube, a single face is 1 centimetre squared, and we have 6 of them, so total 6 centimetre cube. When I put 8 together, remember you've got faces that are hidden. We're not counting those, it's only the outer ones, and we now have a face of 2 by 2, 4 centimetres squared, and again 6 around the cube, so 24 centimetre cube. 8 separate blocks, so that's 8 times the first one, 48 centimetre cubed. So if you break something up, here it's shown you're doubling the surface area. And in terms of collision theory, the red dots of one reactant, when there's a large block, are going to collide, but you'll get more frequent collisions, more successful collisions, if you have a much smaller particle size of the same sample. And then we're going to go on to look at temperature as a factor affecting the rate of a reaction. And the temperature is a measure of the average kinetic energy of the particles in the substance. So it's associated with movement, which is going to lead towards collisions. And at higher temperature, more kinetic energy, greater speed in the particles, and so a greater likelihood of successful collisions. The diagram here, smaller arrows showing motion on the left-hand diagram at a lower temperature, larger arrows, greater kinetic energy at the higher temperature. And so at a higher temperature, more of the colliding particles will have the necessary activation energy, which means that there'll be more successful collisions. And we go on to looking at the factor of concentration. And so here you are just going to have more particles in the same volume. And so the likelihood of the red dots reacting with the blue cubes is going to be much greater at a higher concentration. So you'll have a greater frequency of collision, and from those collisions, more collisions, there'll be more successful ones. And then we look to mechanical mixing, stirring. So can have an effect on heterogeneous reactions in different phases. And indeed, if you've got two materials in the same phase that you've put together and they haven't yet mixed, stirring will obviously help. And on the left, you see the particles separated, some collisions, but once you've stirred and you've spread the particles throughout, you're going to be more likely to have more successful collisions. Looking at a catalyst, remembering a catalyst increases the rate of a reaction and isn't used up, it's going to lower the activation energy, and this will mean that more particles exceed this energy, so more collisions are going to be successful. I'm going to start by looking at energy level diagrams, and here's one without a catalyst. The potential energy of the reactants, the horizontal line, and the products. The products being lower, energy is going to be given out in this particular reaction, so it's exothermic, and the curve between them represents at the peak a reaction intermediate that is formed. The distance between the reactant and product line is the heat of reaction, the enthalpy, delta H, and here, because it's exothermic and the product line is lower, delta H is going to be negative. The activation energy is from the reactant line up to the peak, how much energy has to be added before the reaction can take place. So we're going to put a catalyst in here, and you get the dotted line. You are lowering the activation energy, you're lowering the distance between the reactant and the dotted line peak. The enthalpy remains the same. And if we're looking at the activated complex, the black cross is without a catalyst, and it is easier to make it with a catalyst. The red X, easier to make it, so more reactions are likely. And here are some examples of catalysts. Heterogeneous in all of these cases because they're in different phases. The catalyst is a solid, the reactants gases in these particular reactions, except for aqueous solution in the first one. And you can just read what's reacting and what's formed. And then we looked at something like the nature of a reaction. Some reactions are naturally faster than others, so if you have 3 reactants that need to make an activated complex reaction intermediate, it's going to be harder, so the rate will be lower than if 2 particles have to collide and react together. We can look at pressure, which for gaseous reactions is really equivalent to increasing pressure or increasing the concentration of gas particles. The solvent, if it's in solution, some reactions will take place and the properties of the solvent may affect the rate of a reaction, thinking polarity here. Some electromagnetic radiation and intensity of light. EM radiation is a form of energy. So if you're adding energy to the reaction, you're providing the reacting particles with more energy, and they're more likely to have the activation energy or more in order to get a successful collision. And indeed, with intensity of light, if you're increasing it, some reactions have particles that can absorb more energy, and again, that will increase the rate of a reaction. And finally, an activity using the drawings of 3 diagrams that you've done before. Choose one of the factors and its 3 diagrams. Add 3 more to make a flip book. So remember, with a flip book, you only want to have relatively small changes between one diagram and another to show how that particular factor affects the rate of a reaction.